Hi guys, welcome to week 6. I'm going to give you a little intro of the topic today and what we are going to be going over in the lab. Last week we had taken a look at gravity and orbits, and this week we are taking a look at orbits and Kepler's law. Kepler was an astronomer that lived about the same time as Galileo. He inherited a bunch of observational data from another ancient astronomer named Tycho Brahe. And he made these very detailed observations of the planet Mars. And as he was doing that, he noticed that if the calculations he made for the position of Mars, if it was a circular orbit, didn't match the observations that he actually made. So he inherited about 30 years of observation, made another 30 years of observation, and carefully marked where he observed the planet Mars to be. And he noticed that those observations would not be possible if Mars actually had a circularized orbit. Therefore, the orbit had to be kind of elliptical, like an egg shape. So, here we can see some different orbits here, and we can see that this is actually called a transfer orbit, but we can see the different shapes of orbits. And the consequences of Galileo's law and then these orbital parameters defined by Kepler is that when we launch spacecraft, they don't actually just go straight. Like, we don't go to the moon by just launching straight and going to the moon. We have to use the concepts of these orbits in order to do something called a gravity assist and to actually catch up to the orbit of the next body. So this is showing a gravity assist to get to the asteroid that I actually used in my research, and that it would come around and essentially then catch up to the asteroid here. So we can use these orbital parameters in order to be able to launch things into space. So tonight we are going to be looking at these orbital parameters, and there's some new vocab that you guys are going to be learning. The first is that orbits, we think about them as circles, but there's actually no such thing as a circle. Everything is an ellipse. The moon's orbit around Earth is an ellipse. Earth's orbit around the sun is an ellipse, although a pretty circularized ellipse. And we can calculate the degree of ellipsivity, or we actually call that eccentricity, and it's from a perfect circle, which is a 0, to a straight line, which is 1. So it falls somewhere in between there. So by the end of this, you'll be able to look at an orbit like this and approximate the degree of eccentricity or flattening of the circle. And we can define some locations on the ellipse by where they're located. So if we think about Earth is at a focus of this, and the area that's closest to it is called perigee. Peri, that prefix is close, and further from it is apogee. We can remember because we put a in front, it means opposite. If this were Earth around the sun instead of the moon around Earth, or a satellite around Earth, we would replace perigee with perihelion. So again, it's the prefix that matters. Peri means close. If we put the a in front of it, it's the opposite. So perigee is analogous to perihelion if we're talking about the sun, and apogee is analogous to aphelion if we're talking about the sun. So tonight you're also going to be drawing an ellipse. Although I'm not going to have you guys do this in on actual pen and paper like we would if we were in person. I would have you create one with thumbtacks and a pencil and string. You're going to do this in a simulation. So the first simulation that you are going to go to is looking at similar to what you did last week. However, one of the things that I noticed last week is that when you were looking at Earth and the satellite, and if we click increase, when you increased the space station's mass, you should have seen that the velocity slowed. We could think about this as being like ropes connecting the space station to Earth. If we increase the mass, we increase the number of ropes. We're increasing the frictional force. And the reason we're not seeing a huge change in orbit is simply because the space station in comparison to Earth is so small. Whereas if we look at the moon, we can see a change here if we increase that mass. It's just, different scales. So in your lab tonight, the first thing you're going to go to is that simulation we just looked at. Just make sure you're reading all of your instructions. There are places you're turning gravity on, places you're turning gravity off, and recording the things that you see. Again, no Googleable answers. When you get to part 2, we are looking at the big E here, which is eccentricity. There are 2 simulations that you'll need. You only need this first one here first. And again, if we were in person, I would have you guys draw this. So this is a simulation showing some different parameters of orbits. So if I click play here, we can see that we've got the sun here, and we can make some observations as we click play. Hopefully, if you just run it exactly as it said, you notice some things about this. So notice what happens right here. Hopefully you noticed that the velocity increased. And hopefully you see that out here, the velocity slows down, it decreases. So I'm going to click pause. The reason we have all of these shaded areas is these represent areas that are equal. These are equal triangles. If you actually measured it out and calculated the area of each triangle, they would be equivalent. So Kepler's second law says that a secondary body, whether it's a satellite or a moon or a planet or whatever it is going to sweep equal areas in equal times. So if we take a look if we look at our little blue dot right here, once it moves from here to here, we're saying that takes the same amount of time as it going from here to here. Or is it going from here to here? So let's check that out. And you can actually check this and time it if you like. So it sweeps equal areas in equal times. So that's his second law. So now let's see what happens if I'm going to, let's say I'm going to decrease. Notice what happens to our ellipse. Think about, is it getting more circularized or more elliptical as I'm decreasing the size of the sun? And think about what just happened to our perihelion, because in this case it's the sun, and our aphelion. And I want you to notice that in this simulation, we've got like a grid in the background. That grid is what you're going to be using on your page, because if we were face to face, I would have you creating your own ellipses. You would be using a ruler and you would be measuring the distance across your ellipse. You would be measuring the distance to perihelion, you would measure the distance to aphelion, and you would be identifying some features of your ellipse. So here, you're going to be using these numbers. So we've got 1 meter, 2 meters, 3 meters in order to do that. And you can play with some of the different sizes. So in the lab, you'll see that there are some places where I asked you to do some things. So you will have to take a screenshot of this. So for me, since I have a PC, I'm going to use snipping tool. If you have a Mac, it would be Command, oh gosh, it's been so long since I've had a Mac, Command Alt 4, I think. So I would then take that, but there are places where I've got to, if you see right here, I have to label these locations. So right here, it says take a screenshot of this. Because this is a Google Doc, I'm not just going to take a screenshot. What I'm going to do is go to Google Drawing, and I'm going to say add new, because there are things I have to label here. So I'm going to save and close it because I don't remember what those things are. It might be wise to open this in 2 tabs so you can tab back and forth. So then it says along the planet's elliptical orbit, find the place where the planet is closest to the sun. That's called perihelion, label it P. So I would just open this guy back up, find that location. In this case, I'm going to help you out. It's right here. I would label that perihelion right there. So there are things you're going to be adding to it. So you'll just keep going back to your page and then adding to it. However, make sure you have that screenshot. And then you need to be able to define each of these things. After you've played with this, after you have labeled each of these different areas, then you should be able to define what each of these things are. Your major axis, your semi-major axis, perihelion, aphelion, the focus of the ellipse, and foci, and those are directly related to each other. You could use even the same definition here. So we're just labeling, and I even gave you a picture here of what that is. So then we are using that in order to make some calculations, because then once we have defined the parameters of your ellipse, you can calculate the eccentricity. And in astronomy and in engineering, once we know those things, we can calculate the size of an orbit, we can calculate the distance to a planet, and we know what sort of orbit we would have to get to in order to actually get there. So make sure you guys are reading your instructions, and you just need to follow them. So right here, I defined for you once again. An ellipse is defined. We can find these numbers from the lengths of your two lines, and the distance between the foci is the length of Q minus the length of little q. So again, you just got to make sure you're reading your instructions. And then I gave you right here how to calculate that. So your eccentricity, or E, equals your F divided by your D. So eccentricity, like I said before, ranges from 0 for a perfect circle to 1 for a flattened ellipse or a straight line. Then using your diagrams, make sure you are filling in the real data for your ellipses. You would have created 2, because back up here, you'll create your first ellipse, but it says you're going to create 2. You're going to do the same thing for each. So this could be my ellipse number 1. Then if I go back here, I'm going to change this distance. I'm going to make it super close together. This would be my ellipse 2. So I'm doing the same thing to each image. So you have to have that data, and then we're plugging that in right here, ellipse 1, distance from perihelion to sun. And again, you're using the numbers in that grid. Right here, you should have already had labeled your big Q and your little q. You should have had each of these things labeled there. Oops, looks like I moved them. Sorry, I'll make sure that's fixed. And then how to show your eccentricity. So you just move across the table. So again, this is why you can't divide and conquer and have one person do one part while you do another, because it just will not work. Then we're taking that and we're applying that to the solar system. So for every planet in our solar system, the orbit that orbits the sun in an elliptical path, there are varying degrees. So we're using this data. So again, this would be like if we had a diagram of that. So we have the distance from perihelion to the sun, and then from aphelion to the sun, which again define our semi-major axis, or our distance across that orbit. So here we can see that one of those is labeled big Q, the other is little q. We subtract them to get our F value, then we add them to get our D. We divide those two to get our eccentricity. So we need both of those things. Then you have some questions, and you can check what you got here, but I have to see that you have done those calculations. Finally, we are taking a look at some pictures of some orbits. So in here, we're directly looking at and trying to make some comparisons. Like if we have an eccentricity of 0.016, that's very, very, very circular. Which one would that be? Compared to this trans-Neptunian object, which is 0.8, very, very high eccentricity, which would that be? When we get to part 2, you will need to, you can use like an online ruler, you can use, you will actually physically need to measure the distance between your two foci and get that, and then you can use either this calculation or the one you used before. It's actually, you get the same number. Previously you measured all the way across. This one you're measuring between foci. You will end up getting the same answer. I don't care which method you choose. You can find either method online. They yield the same answer to get your calculated eccentricity. Then here we're taking a look at this orbital diagram, labeling where each of these things happen. We're restating Kepler's second law in our own words. Then we're taking a look at these two different ellipses that have a different value for your A, because in Kepler's third law, if we know the distance of one, we can tell the orbit of the other. Or if we know the orbit of one, we can tell the distance of the other. But if we know our P, which is the period of the orbit, if we square that, it's equal to the A, or the semi-major axis, cubed. So if we know one, we know the other. So if they have the same value for A, you should be able to tell what that means for their values of P and how the heck that could possibly happen based on this. So we're using that equation to be able to explain it. So we don't have to necessarily solve it, but being able to explain it. And then you have some analysis and then applying it to an actual orbit here of a satellite. Make sure that you are defending your answers. Sometimes you guys are not following up with that explanation, and that is definitely losing you some points. All right, I will see you guys tonight.